So this another application, electric field due to a uniformly charged non-conducting sphere. Already we discussed previous application, conducting sphere. This one is a non-conducting sphere. Previous application, conducting sphere. In conducting sphere, inside the electric field are 0, outside the electric field k cube by r square. R is nothing but sphere radius, conducting sphere radius. Outside the electric field strength is equal to k cube by x square. X is nothing but center of the conducting sphere to the point, Gaussian surface point, is distance is x. So here non-conducting sphere and conducting sphere, only one is the different. Inside the electric field not equal to 0 in the non-conducting. Conducting sphere, inside the electric field 0. Remaining two cases are same. In outside and inside the electric field strength same. Conducting and non-conducting sphere. For x is bigger than capital R, nothing but outside the electric field. Here the outside the electric field strength is equal to k cube by x square. Now second condition, for x is equal to r case means on-side or surface conducting sphere. So ES is equal to k cube by capital R square. In third case, for x is smaller than capital R. It means let us consider this one is a small non-conducting sphere. Means inside this some charges are there. So in here this conducting sphere radius capital R, this density rho, nothing but coulomb for meter cube. Coulomb for meter cube. So let us consider this is one Gaussian surface. This Gaussian surface distance to point P is, I would like to consider x. So here the inside. Here the Q, total charge capital Q, total enclosed charge capital Q. But here inside this small elemental charge we want. This Q enclosed charge is equal to total charge by volume 4 by 3 pi capital R cube into small elemental volume. So here 4 by 3 pi into x square. X is nothing but Gaussian surface radius. So 4 by 3 get cancelled, pi also get cancelled. Q enclosed is equal to x cube divided by r cube. X cube divided by r cube. So this is a Q enclosed. So according to using Gaussian or Gauss law, surface M. Let us consider this surface M. So using Gauss law, closed integral of surface M into E bar dot ds bar is equal to Q enclosed divided by epsilon naught. So here Q enclosed closed integral of M into E bar dot ds bar is equal to enclosed charge is equal to Q into x cube divided by r cube. Q into x cube divided by r cube into epsilon naught. Here the electric field, uniform the electric field, and ds and electric field both are same direction, angle 0, cos 0, 1. That's why electric field you may write out of the integral. Closed integral of M into ds is equal to Q into x cube by r cube into epsilon naught. Closed integral ds nothing but area, small spherical area, Gaussian surface, inside the Gaussian surface spherical area, that area is nothing but 4 into x square is equal to Q into x cube divided by r cube into epsilon naught. X square get cancelled. So final electric field strength at point P is equal to, this point P is nothing but inside the non-conducting sphere is equal to qx divided by 4 pi epsilon naught r cube r cube. So this one similarly here multiply and divided by 3, value won't change. 4 by 3 into 3 pi epsilon naught r cube. So this one nothing but 4 by 3 pi epsilon naught, this value is nothing but so inside the electric field nothing but q x divided by 4 by 3 pi r cube into 3 epsilon naught. 4 by 3 pi r cube, cube by 4 by 3 pi r cube nothing but charge density. Charge density q in electric field strength inside is equal to rho x divided by 3 epsilon naught, that should be is equal to also qx divided by 4 pi epsilon naught into r cube. This formula very important while doing numerical problems. Here another application, electric field due to a uniformly charged wire. Wire nothing but a long wire. Wire nothing but one dimensional wire. Here let us consider small wire, small thick, very this thickness very small. Here the charge positive infinity wire. You may draw the first Gaussian surface. Like this Gaussian surface look like a cylinder. This cylinder got cylinder length L and this point is a P. So here from center of the wire to the point P, that is this distance, I would like to consider R. Here the electric field out of the this direction, out of the, because here positive charge, electric field direction and normal to the outside. So here a small elemental ds, this ds direction also area is a vector, that's why this electric field and ds direction both are same. This is the first surface, this is the second surface, now this one is the third surface. Here important point, in first point surface phase 1 and 3, this one look like a circular, so circular surface and surface to lateral surface. So here the electric field direction, this is the electric field direction, first circular surface, and here the area vector ds like this, both are 90 degrees. Here the electric field get cancelled, and third surface, here the electric field direction, now here the ds direction, this small elemental, so this is the dA direction. Here are the angle 90 degrees, so cos 90 is 0, that's why first and third surface area total net electric field 0. So here according to, you may apply here Gauss law. Using Gauss law, closed integral of this one is a surface M, closed integral surface M, E bar dot ds bar is equal to q enclosed divided by epsilon naught. Total enclosed, here total nothing but how many surfaces are there? 3 surfaces. Sum of integral of first surface into electric field into ds bar plus second surface into electric field into ds bar plus third surface into electric field into is equal to q enclosed by epsilon naught. So here the electric field and the surface area, these two are perpendicular each other. That's why here electric field won't exit total. Here the E dot ds value become to 0, and here also similarly 0. Here finally integral of second surface into ds bar is equal to q enclosed divided by epsilon naught. Q enclosed nothing but charge density into unit length. Charge density into unit length. Charge here because into length. Why I am saying here length nothing but here wire nothing but one dimensional. Wire nothing but one dimensional. So one dimensional charge enclosed is equal to charge density into length. If two dimensional charge enclosed is equal to area density or sigma into charge density. Two dimensional charge density sigma into area. If three dimensional charge density is we consider rho. So enclosed charge is equal to rho into volume. Keep that 3 points. So enclosed is equal to lambda L by epsilon naught. So electric field constant, you may write out of the integral into ds is equal to lambda L divided by epsilon naught. Here the total area, total ds nothing but area. So here one dimensional. Here the one dimensional. So one dimensional area is nothing but this small distance is L. So area is nothing but length into this L. So electric field into this one cylindrical area is nothing but 2 pi r into L is equal to lambda L by epsilon naught. L get cancelled. So electric field strength due to point P is equal to lambda divided by 2 pi r epsilon naught. 2 pi r epsilon naught. Otherwise here multiply and divided by 2. Here multiply and divided by 2. So electric field strength due to point P is equal to 2 lambda by 4 pi epsilon naught into r. So is equal to 2 lambda by 2 k lambda by r also. This is the electric field strength due to point P, the uniformly charged wire. Here another application, electric field due to a uniformly charged metal cylinder. So here also uniformly charged. Let us discuss electric field due to a uniformly charged metal cylinder. Here specifically we will talk about a very long metal cylinder. Let us consider this a very long metal cylinder. This one is the center. Here the radius is a capital. So here the very long metal cylinder. And we already know that in case of a metal cylinder, when the charges are distributed, it will only be distributed on the outer surface, and as being a cylinder, a uniformly symmetric object, charge will be uniformly distributed. So obviously it will be uniformly charged, and in case of a metal cylinder, we already are aware about for a position x less than small r inside the electric field, inside the electric field is always zero because symmetry, that's why inside the electric field always zero, because it is about the exterior point because of symmetry. We will calculate it by using a Gauss law. Let's have a look on this picture. So let us consider this point P. Due to this point P, you may draw the first Gaussian surface. This Gaussian surface look like a cylindrical. This cylinder length already considered L, and this charge density sigma nothing but coulomb for meter square. Here also three surface area, first one, second one, and third one. Here also first point, surface 1 and 3, circular surface of the Gaussian surface. Circular surface of that of circular surface of the Gaussian surface. And second one, surface to lateral surface of the Gaussian surface. Here by using Gauss law, for the Gaussian surface M, this one is the Gauss. By using Gauss law, so closed integral of M is into E bar dot ds bar is equal to Q enclosed divided by epsilon naught. Here total charge is nothing but integral of first surface into E bar dot ds bar plus integral of second surface into E bar dot ds bar plus integral of third surface into E bar dot ds bar is equal to Q enclosed by epsilon naught. Here the electric field, this is the point P. Here to here, this distance outlet you consider small r, O or x also no problem. Small r or x also no problem. So here the electric field, this is the direction of the electric field. Here the small elemental area, this direction ds bar, both are same. Here the electric field in first surface, circular surface electric field, this is the direction, and the surface direction, this is the surface area direction, and the third charge electric field, this is the electric field direction, and the third surface area, this is a surface area direction, this is a small surface area. So in first and third surface area and electric field both are 90 degrees. That's why this electric field also 0, this electric field also 0. Integral of second surface E bar dot ds bar is equal to Q enclosed nothing but charge density into that area. Area is nothing but pi r in pi 2 pi r into L. So here charge density and here sigma into 2 pi capital R L divided by epsilon. Q enclosed is equal to sigma into 2 pi R into L. Charge enclosed, already I said charge enclosed into in two-dimensional two-dimensional sigma charge density, sigma into area. Area is nothing but 2 pi r l, 2 pi r l. So here the electric field uniform, the electric field you may write out of the integral ds is equal to sigma into 2 pi rl divided by epsilon naught. Closed integral of or integral of ds in second phase is nothing but here the length of the cylinder and this length is nothing but electric field into field strength into 2 pi small r into L is equal to sigma into 2 pi capital R into L divided by epsilon naught. L get cancelled, 2 pi get cancelled. Electric field strength is equal to sigma into capital R by small r into epsilon naught. Small r into epsilon naught. This one is a very important case, very important. This is well, or sometime you may write r, if r is equal to x case, electric field strength at point P is equal to sigma into capital R by x into epsilon naught also. This formula valid for x is bigger than or more than the capital R case. It means for x is bigger than capital R or small r is bigger than capital R. This case only valid for this equation. Okay. Now another application, electric field due to a long uniformly charged non-conducting cylinder. In conducting cylinder already we discussed previous. So let us discuss the electric field due to the uniformly charged non-conducting long cylinder. The figure shows a long cylinder of radius, let us consider capital R, so which is uniformly charged in its volume density or charge density sigma rho, charge density rho. So charge density is equal to here three-dimensional diagram, so that's why charge density is nothing but charge by volume. So SI units, charge nothing but coulombs and volume nothing but meter cube. Charge coulomb for meter cube. And here say we are required to find the electric field strength in its surrounding. Then in this situation for outside region, that is say at a point for x is bigger than the capital R. Let us consider this one is a long cylinder. This one is a long cylinder. This center of the cylinder, long cylinder wire. This radius is a capital R. Here the charge is inside the charge. Here the charge. So first of all, you may draw the Gaussian surface. This cylinder length L, this point is P, at this point center to this point P, this distance outlet to consider X. Outlet to consider X over R also no problem. R, so is equal to R also no problem. Here the cylinder radius capital R and the cylinder length L and the distance center to the cylinder center to this point P. Here you may find the electric field in first case. So for X is bigger than capital R or small r is bigger than capital R, nothing but outside the electric field at Gaussian surface. Here also three surfaces there, 1, 2, 3rd surfaces. In these three surfaces, and first one and third one is nothing but already we discussed in previous also. First one and third one nothing but circular surface, and the second one nothing but lateral surface of the Gaussian surface. Of using Gauss law for, let us consider this surface. Gauss law for surface M. Surface M. So here the according to class closed integral of M into E bar dot ds bar is equal to Q enclosed divided by epsilon naught. Here the Q enclosed is equal to, here the charge density, let us consider this rho coulomb for meter cube. Coulomb for meter cube. Enclosed charge is equal to charge density into volume. Charge density into small elemental volume. The elemental volume nothing but 4 area into length. Area nothing but pi r square. Pi r square into length. So here the electric field also three diagrams. So three surfaces, first, second and third. First one and third one get cancel each other. Only here exists second surface, already we discussed previous only. So total electric field at first surface plus electric field second surface in plus third surface E bar ds bar is equal to Q enclosed by epsilon naught is equal to density into pi r square into L by epsilon naught. Enclosed charge is equal to charge density into value. Value nothing but area into length. Area nothing but pi r square into length. So this one become to 0. This one also become to 0. So electric field you may write out of the integral. The second surface is equal to rho into pi r square L divided by epsilon naught. Integral ds nothing but area of the cylinder. Area of the cylinder nothing but 2 pi RL. So here to here distance is the R. So electric field into 2 pi small r into L is equal to rho into pi capital R square L divided by epsilon naught. Pi get cancelled, LL get cancelled. Electric field is equal to rho R square by 2 epsilon naught R. 2 epsilon naught R. If is equal to, if R is equal to X, electric field is equal to also rho R square by 2x epsilon naught. This one also valid. This one also valid. Next case, for inside the Gaussian surface. Inside the Gaussian surface. Inside the Gaussian surface, what happened? So here the inside the Gaussian surface. Next case, inside the Gaussian surface. So let us consider this cylinder. This radius is R. Charge. Here draw the Gaussian surface. Inside the Gaussian surface. Here inside the Gaussian surface. This Gaussian surface. So here to here, this one is the x distance, the radius, and this Gaussian surface cylinder length is L. L. Here the case for x is smaller than the capital R, means inside the Gaussian surface. Using Gauss law for surface M. Let's consider this surface M using Gauss law for surface M. So total enclosed electric field into ds bar is equal to Q enclosed by epsilon naught. Here the Q enclosed is nothing but sigma here inside the x distance. So here electric field you may write out of the integral, and integral ds is equal to sigma density, charge density rho into area x pi x square into length divided by epsilon naught. Here closed integral of ds nothing but area inside the area. Inside the area is nothing but 2 pi x into L. So here the electric field 2 pi x into L is equal to rho into pi into x square L divided by epsilon naught. L get cancelled, 1x get cancelled, pi also get cancelled. So electric field is equal to rho x divided by 2 epsilon naught. This one is the inside the electric field strength, non-conducting cylinder. Let us discuss another application. Electric field due to a large uniformly charged sheet. Let's discuss the electric field due to a large uniformly charged sheet by using a Gauss law. If this a large uniformly charged sheet which is having a charged per unit area sigma, charge per unit area nothing but sigma nothing but coulomb for charge nothing but coulomb area nothing but meter square, charge for a coulomb for meter square, and say due to this sheet in front of the it's a point P or so here this is the sheet, this one is the sheet. So here the charge density sigma and coulomb for meter square. Here the point P. Due to this point P, you may draw the Gaussian surface like this. This is the Gaussian surface. So here you may write the left side also same distance from the center of the Gaussian, and here also Gaussian surface, but this point let us consider P dash. This point let us consider P dash. Here the electric field direction, this is the electric field direction. Here the small elemental area direction, ds direction. Elemental area, ds direction. Here also electric field direction, this is the electric field direction, and this one also small elemental area, this is also ds bar direction. So here electric will be parallel. This electric field and area both are parallel direction. Here you may apply Gaussian surface using the Gauss law on surface M. Using here Gauss law for surface M. Gauss law for surface M. So what is the formula? Closed integral of M into E bar dot ds bar is equal to Q enclosed into Q enclosed by epsilon naught. Q enclosed nothing but so charge into already charge density into surface area. This total surface area I would like to consider yes. So charge density into S divided by epsilon naught. Electric field, uniform electric field, you may write out of the integral. Here also this total electric field into ds. Here also 3. This is the first region, this is the second region, this is the third region. So 1 and 3 circular surfaces and 2 is nothing but lateral. So here the surface, here the electric field direction, this electric field direction, here the ds direction, both are opposite direction. That's why second surface electric field is equal to 0, net electric field is equal to 0. It means into first one into electric field into ds bar plus integral of second surface into E bar dot ds bar plus integral of third region E bar dot ds bar is equal to sigma S divided by epsilon naught. This second one become to 0 because electric field angle between electric field and surface area is theta is equal to 90 degrees. That's why second region electric field, this value become to 0. Remaining electric fields, so integral of first electric field into ds plus third surface electric field into ds bar is equal to, so sigma into s divided by epsilon naught. Here both are same, so here that's why 2 into electric field, uniform electric field, you may write out of the integral into ds is equal to sigma s divided by epsilon naught. Integral ds nothing but total area we consider already, we consider s. So 2 into electric field strength into s is equal to sigma s divided by epsilon naught. S get cancelled. So electric field strength due to point P is nothing but sigma by 2 epsilon naught. Sigma by 2 epsilon naught. Very important formula. So here another application, electric field due to large uniformly charged metal sheet. Metal sheet nothing but charge accumulated on surface of the metal sheet. Let us consider this one is a one metal sheet. So here the charge accumulated on metal sheet. So this is the center of the metal sheet, and let us consider the one point. This point is P. So you may draw the Gaussian surface here. So this is the Gaussian surface line. So and inside the electric field become to 0 because of the Q enclosed is equal to charge enclosed is equal to 0. Charge enclosed is equal to 0, nothing but symmetry property here. Here the charge become to here the charge, both are same and opposite direction. That's why inside the electric field 0. Electric field 0. Here the first surface, this is the second surface, this is the third surface. In third surface and second surface become to 0 because third surface inside the electric field become to 0. In second surface, this is the direction of the area, small elemental area, and electric field direction. This is the electric field direction and small elemental area direction. Ds bar also same. Here the ds bar direction. Here using Gauss law for surface M. Let us consider this surface M. So closed integral of M into E bar dot ds bar is equal to Q enclosed by epsilon naught. So let us consider this area S. So Q enclosed nothing but here also 3 first surface electric field into ds bar and second surface electric field into ds bar plus third surface electric field into ds bar should be is equal to Q enclosed nothing but here the charge density. This charge density sigma nothing but coulomb per meter square. Sigma into S. Charge enclosed charge is equal to charge density into area divided by epsilon naught. Here the second one and the third one become to the here this region, third region electric field, inside the electric field become to 0. That's why this total integral of E dot ds is equal to 0, and the second one angle between electric field and ds is 90 degrees. That's why this total second region electric field strength is equal to also 0, and integral of first into E dot ds is equal to sigma into S divided by epsilon naught. Here uniform electric field you may write out of the integral first into ds is equal to sigma into S divided by epsilon naught. Electric field strength is into closed integral of ds nothing but total area. Here total area already we consider S. So into S is equal to sigma into S divided by epsilon naught. S get cancel. Electric field due to point P sigma by epsilon naught. Sigma by epsilon naught.